In 1940, every fighter designer in the Western world agreed on one thing. You do not hang a radiator scoop off the belly of a high-speed aircraft. You tuck it away. You minimize it. You hide it from the airflow, because every pound of drag it creates is a pound of thrust your engine will never get back. Edgar Schmude did the opposite. He was a self-taught German immigrant working at North American Aviation in Inglewood, California. No university degree, no published papers, no reputation outside his own drafting room, and he had just been given 120 days to design a fighter aircraft from scratch for the British, who were losing the war and running out of airplanes. Schmude put the radiator exactly where nobody else would have put it. He hung it out in the open, underneath the fuselage, behind the cockpit, where every aerodynamicist who looked at the drawings said the same thing. That scoop will destroy the airplane's speed. But Schmude had read a paper, a dry, mathematical British technical report published 5 years earlier by an engineer nobody had heard of. That paper said something that sounded impossible. It said waste heat from a properly designed radiator duct could produce thrust, not drag, thrust. The cooling system could push the airplane forward. Every other designer had read the same paper and set it aside. Schmude read it and bet his entire career on it. He was right. But it would take 4 years, one crash, one wrong engine, and 30-minute test flight by a pilot from the wrong company before anyone else understood what he had done. To understand why Edgar Schmude would make that bet, why he would stake his career on a paper the entire aviation industry had ignored, we have to go back 5 years before the Mustang existed. We have to go to a research building in southern England, where a quiet engineer was about to write the most important document that nobody read. In 1935, at the Royal Aircraft Establishment in Farnborough, a British engineer named Frederick William Meredith was working on a problem that the entire aviation community had accepted as permanent, a limitation you designed around the way you designed around gravity. The problem was cooling. Every liquid-cooled piston aero engine produced an enormous amount of waste heat. The way you dealt with that heat was simple and expensive. You pumped engine coolant through a radiator. You forced air through the radiator. The air carried the heat away, and the process of forcing that air through the radiator created drag, significant drag, unavoidable drag. The drag was the price of keeping the engine alive, and every designer in the world paid it the same way. You tried to make the radiator as small as possible. You tucked it into the wing. You buried it behind the propeller spinner. You did everything you could to hide the radiator from the airflow, because every square inch of radiator surface exposed to the wind was a square inch of performance you would never get back. Meredith asked a question that no one else seemed to be asking. What if the waste heat is not waste? He published a technical report, British Aeronautical Research Council Reports and Memoranda number 1683, titled Cooling of Aircraft Engines with Special Reference to Ethylene Glycol Radiators Enclosed in Ducts. The title alone was enough to put most readers to sleep. The mathematics inside were dry, dense, and carefully conservative. But what the paper said, if you read it with an engineer's patience, was revolutionary. Meredith demonstrated that if you designed the cooling duct with deliberate precision, if the air entered through a carefully shaped intake, slowed down inside a diverging diffuser section, passed through the radiator matrix under controlled pressure, and then exited through a convergent nozzle at the rear, something unexpected would happen. The waste heat absorbed by the air, passing through the radiator, would cause that air to expand. The expanding air forced through the narrowing exit nozzle would accelerate, and the exhaust stream, leaving the back of the duct, would be moving faster than the intake stream entering the front. The difference in velocity meant a difference in momentum, and a difference in momentum, in the language of physics, is thrust. The cooling system could function as a crude, low-temperature ramjet. It would not produce enough thrust to propel the airplane by itself. But it could, if the duct geometry was precise enough, recover most of the drag the radiator created. Perhaps nearly all of it. The aviation industry read the paper. A few engineers nodded politely. And then the world moved on. The Supermarine Spitfire, then in development, incorporated a mild version of the concept. Its radiator sat in a duct under the wing, partially shaped to encourage some thrust recovery. But the Spitfire's duct was not designed to extract maximum performance from the Meredith effect. It was a concession to the idea, not a commitment to it. The Messerschmitt Bf 109 used similar principles in a similarly cautious way. Nobody was willing to bet a fighter's entire performance envelope on a theory published in an obscure government memorandum by an engineer who was not famous and would never become famous. Nobody, that is, except one man who would not read the paper for another 5 years. A man who, when he finally did read it, would see something in it that every other designer had missed, not because he was smarter than they were, but because he was desperate enough and methodical enough and stubborn enough to follow the mathematics all the way to the end. That man was sitting in a drafting room in Inglewood, California, in April of 1940, waiting for a question that was about to change his life. France was collapsing. The Wehrmacht had begun its thrust through the Ardennes, and the speed of the German advance was shattering every assumption the Allied High Command had made about the pace of modern war. Britain was staring at the real possibility of fighting alone. The Royal Air Force was burning through Spitfires and Hurricanes at a rate that British factories could not sustain. And so a delegation called the British Purchasing Commission, led by Sir Henry Self, crossed the Atlantic and began knocking on doors at American aircraft companies with a single, urgent request. Build us the Curtiss P-40 Warhawk under license. As fast as you can. We need fighters. One of the doors they knocked on belonged to North American Aviation, a company that had built its reputation on training aircraft, not combat fighters. The man who answered was James Howard Kindleberger, known to everyone as Dutch. He was 45 years old, a self-made aviation executive who had assembled North American from almost nothing into a company capable of serious production. But Dutch Kindleberger had never built a frontline fighter. His company made the PT-6 Texan, the trainer that taught half the Allied world to fly. The British were not asking him to innovate. They were asking him to copy someone else's airplane. Kindleberger walked down the hall to a drafting room where his chief designer was working. Edgar Schmude was 41 years old. He had been born in 1899 in Hornbach, a small town in the German Palatinate. He had taught himself aeronautical engineering without attending a university. He had worked at the Fokker Aircraft Company before emigrating, eventually arriving in the United States and joining the organization that would become North American Aviation. He was, by every available account, a quiet man, methodical, obsessive about detail, exactly the kind of undramatic engineer that nobody makes movies about and nobody remembers after the war is over. But Schmude had been doing something in that drafting room that nobody outside North American knew about. For years, while the company built trainers, Schmude had been privately studying fighter aircraft design. He had analyzed the Spitfire. He had studied the Messerschmitt. He had read Meredith's 1935 paper And unlike every other designer who had read it and set it aside, Schmude had kept thinking about it. He had not dismissed the Meredith effect as theoretical elegance with no practical future. He had been quietly working out how to build an airplane around it. Kindleberger asked him one question. According to Schmude's own later account, preserved in his personal papers, the question was simple. Did want to build P-40s at North American? Schmude's answer has become part of aviation history. He said they should not build an obsolete airplane. They should build a new one. That was the entire conversation. Kindleberger went back to the British and made a counteroffer that no sensible businessman should have made. He told Sir Henry Self that North American aviation could design a completely new fighter from scratch, engineer it, build a working prototype, and have it flying in 120 days. For context, the Lockheed P-38 Lightning had taken roughly 2.5 years from concept to first flight. The Republic P-47 Thunderbolt, nearly 3, had taken nearly thickly. Kindleberger was offering to compress the same process into the British, who were running out of options along with airplanes, agreed. The contract was signed in May of 1940. The clock started, and Schmude, the moment the contract was signed, began making the decisions that would define the aircraft and nearly destroy his reputation. The first decision was the radiator. Every liquid-cooled fighter in the world faced the same penalty. Lee Atwood, North American's vice president and one of the core members of Schmude's engineering team, explained the mathematics decades later in an article published in Aeroplane magazine in May 1999. At full power, Atwood wrote, the propeller of a Mustang produced approximately 1,000 pounds of thrust. The cooling drag from the radiator was on the order of 400 pounds. Nearly half of every pound of thrust the engine generated was being consumed just to keep the engine from destroying itself with its own heat. That was the central problem facing every liquid-cooled fighter in 1940. Not horsepower, not armament, cooling. And every designer in the world addressed it the same way. Minimize the radiator. Tuck it out of the airflow. Accept the drag penalty and try to keep it as small as possible. Schmude went the other direction entirely. He placed the aircraft's primary cooling radiators in a large scoop underneath the fuselage, well behind the cockpit, hanging down into the airstream where every aerodynamicist who saw the drawings would say the same thing. That scoop will add so much drag, the airplane will never reach the speeds it needs. But Schmude had done the calculations. He had taken Meredith's 1935 paper and applied it not as an afterthought, but as the organizing principle of the entire rear fuselage, the intake shape, the internal diffuser angle, the radiator matrix, the exit nozzle. Every dimension of that belly duct was computed to extract the maximum possible thrust recovery from the waste heat of the engine's cooling system. According to Atwood's figures, the goal was staggering. Against 400 pounds of raw cooling drag, the properly designed Meredith duct would produce roughly 350 pounds of thrust. Net cooling drag would drop from 400 pounds to approximately 50. An 85 to 90% reduction in the single largest drag penalty any liquid-cooled fighter had to pay. North American did not have their own high-speed wind tunnel, so they rented the 10-foot Guggenheim wind tunnel at the California Institute of Technology and ran their duct designs through it. They refined the intake geometry. They adjusted the diffuser. They test exit configurations. They treated the cooling system not as an engineering afterthought, the way every other company treated it, but as a primary structural and aerodynamic component of the aircraft. part of the propulsion system itself. The second decision was the wing. Schmude chose a laminar flow airfoil, the NAA NACA 45100 profile, developed jointly with the National Advisory Committee for Aeronautics. Laminar flow airfoils were a new idea. The theory said that if the wing surface was smooth enough, the air flowing over it would remain in orderly layers, laminar layers, rather than tumbling into the chaotic turbulence that created drag on conventional wings. In a wind tunnel, the concept worked beautifully. On a production aircraft covered in rivet heads, panel seams, paint, and the accumulated grime of combat operations, no one had ever proven it could work at all. Other designers looked at the laminar flow data and decided the gap between theory and production reality was too wide. Schmude looked at the same data and committed to it, not because he was reckless, because the airfoil shape that produced laminar flow in theory also happened to be an exceptionally clean, high-speed profile even when the laminar flow broke down. It was a wing designed for one purpose that Schmude suspected would deliver a different purpose entirely. He did not say this publicly. He committed to the laminar flow promise, because that was the language the aerodynamics community understood. But the shape of the wing was the real bet, not the laminar flow. Two decisions: a radiator in the worst possible location, a wing built on an unproven theory. Both choices made under a deadline that was ticking towards zero. The team did not need the full 120 days. The prototype, designated NA-73X, with civil registration NX-9998, was rolled out onto the ramp at Mines Field, the airfield that is today Los Angeles International Airport, exactly 102 days after the contract was signed. It sat there, with borrowed wheels from an 86 trainer, with wooden dummy exhaust stacks glued to the cowling, because Allison had not yet delivered the V1000 710 engine, and it was photographed for the newspapers, looking like an airplane that was not quite finished. Because it was not quite finished. When the engine finally arrived and was installed, a freelance test pilot named Vance Brees climbed into the cockpit on October 26, 1940, and took NA-73X into the air for the first time. 5 minutes. Then he landed, checked the airplane over, climbed back in, and flew again for another 10 minutes. 2 flights in one day. The airplane that every expert said should not exist was flying. 25 days later, it was destroyed. On November 20th, 1940, Paul Balfour, North American's chief test pilot, was assigned to fly NA-73X on a high-speed evaluation run. According to the account Schmude preserved in his personal notes, he offered to walk Balfour through the cockpit procedures before the flight: the fuel system, the tank selectors, the sequences. Balfour declined. One airplane, the account records him saying, was like another. 12 minutes into the flight, the Allison engine went silent. Balfour had not switched to the reserve fuel tank. The main tank ran dry. He brought the airplane down into a plowed field west of Lincoln Boulevard. And the prototype, the only existing example of the aircraft that would become the most consequential fighter of the war, caught a furrow and flipped onto its back. The propeller bent. The canopy cracked. The airplane that had taken 102 days to build had accumulated 3 hours and 20 minutes of total flight time. Schmude had offered to explain the cockpit. The pilot had refused. The airplane did not fail. A human decision failed. The Mustang program could have died in that field. There was every institutional reason for it to die. The prototype was wrecked. The design was controversial. The radiator scoop that Schmude had staked everything on was being discussed in engineering circles as confirmation that North American had gambled and lost. The program did not die. The airplane was hauled out of the dirt, disassembled, and rebuilt. A new chief test pilot, named Robert C. Chilton, took over the flight test program. And when Chilton got into the rebuilt NA-73X and flew it, he left a note in his own records that has survived. He wrote that the airplane was clean flying. He wrote that it had no bad vices. He said it flew and handled better than any fighter then in American service. A plane designed in 102 days. A plane that crashed on its fifth flight because a test pilot would not listen to the designer. A plane that was rebuilt from wreckage and then outperformed everything else in the sky. The engineers at North American understood what they had. They understood that the belly scoop, the thing every aerodynamicist had called a catastrophe, was doing exactly what Frederick Meredith's mathematics said it would do. The hot air leaving the duct was pushing the airplane forward. The scoop was not a drag penalty. It was a thrust source. If those calculations held, then everything the aviation world believed about fighter design was about to become obsolete. But the Mustang had a problem that no amount of brilliant engineering could fix. A problem that by the spring of 1942 would make it look like the entire program had been an expensive, elegant dead end. Because the engine was wrong. The Allison V1710 was a good engine. That needs to be said clearly, because what happened next was not the engine's fault. It was reliable. It was cheap. It was American. It produced approximately 1,150 horsepower at low altitudes, and it ran cleanly for hundreds of hours between overhauls. Mechanics liked it. Pilots trusted it. As piston engines went in 1940, the Allison was a perfectly respectable piece of American engineering. And it had a limitation that would nearly kill the Mustang program. This was not a choice Edgar Schmude made. This is important to understand because the first two engineering decisions, the belly radiator and the laminar flow wing, were deliberate. Schmude chose them. He calculated the risks. He accepted the consequences. The Allison engine was different. The Allison was what was available. When Kindleberger promised the British a prototype in 120 days, there was exactly one American liquid-cooled engine that could be delivered on that schedule, the Allison V1710. There was no second option. There was no fallback. Schmude designed his airframe around the only engine the timeline permitted, and he moved on to the problems he could control. The engine worked as advertised at the altitudes it was built for. Below 15,000 feet, the Allison Mustang was a revelation. The RAF took delivery of the first production batch, 320 airframes designated Mustang Mark I, and the pilots who flew them at low altitude began report numbers that confused their own analysts. The Allison Mustang was faster than the Curtiss P-40 Warhawk. Significantly faster. At 20,000 feet, it was approximately 30 miles per hour quicker than the P-40. Same engine, same horsepower, same fuel. The only difference was the airframe wrapped around it. The Spitfire Mark V, which had a better engine, a Rolls-Royce Merlin producing more horsepower, was slower than the Mustang at low altitude. Airplane that every aerodynamicist had dismissed because of its belly scoop was outrunning a Spitfire, and the reason was hanging underneath its fuselage. That radiator duct, the one every expert had called a mistake, was doing precisely what Meredith's 1,935 paper predicted it would do. The cooling system was recovering drag as thrust. The airframe was being pushed forward by its own waste heat. Schmude's first bet was paying off. The belly scoop worked. The Meredith effect was real, and almost nobody noticed, because the Allison had a problem that buried everything else. Above 15,000 feet, the Allison died. Not instantly, not dramatically. What happened above 15,000 feet was quiet and mathematical and lethal. The Allison V1710 had a single-stage supercharger. A supercharger is a compressor. It squeezes thin high-altitude air into something dense enough for the engine's cylinders to burn. The Allison supercharger was designed for export. It was deliberately kept simple, and its compression capacity ran out at about 15,000 feet. Above that altitude, it could not force enough air into the engine. Horsepower began to fade. At 20,000 feet, it fell sharply. By 25,000 feet, the Allison Mustang was gasping, producing a fraction of the power it made at sea level, struggling to hold speed, struggling to climb. And the air war over Europe was being fought at 25,000 feet and above. The Luftwaffe's frontline fighters, the Messerschmitt Bf-109F and G models, the Focke-Wulf FW-190, were optimized for high-altitude combat. Their superchargers were designed for exactly the altitudes where the Allison collapsed. American and British bombers cruised at 25 to 30,000 feet. The Spitfire Mark 9, powered by a Rolls-Royce Merlin with a two-stage, two-speed supercharger, could fight effectively at those altitudes. The Mustang could not. The Royal Air Force looked at the Mustang's performance envelope, drew a line at 15,000 feet, and assigned the airplane to missions that kept it below that line. Low-level tactical reconnaissance, ground attack, shooting up German trains and trucks and supply convoys in France. Work that any competent airplane could do. Not the work that Edgar Schmude had designed this airframe to do. The fastest Allied fighter at low altitude was being used as a ground attack airplane. The most aerodynamically advanced airframe in the world was strafing locomotives. The belly scoop was proof beauty itself every time the Mustang outran a Spitfire below 15,000 feet, and nobody cared, because the war was not being fought below 15,000 feet. By the spring of 1942, there was a real and growing possibility that the P-51 Mustang would go down in history as a clever piece of engineering attached to the wrong engine. A beautiful airframe wasted on a mission it was not built for. The critics who had said the radiator scoop was a mistake were not quite right. But they felt vindicated anyway, because the airplane was not doing what Schmude had promised it could do. Schmude had designed a fighter that could, with the right engine, outperform anything in the sky. The right engine did not exist in his airplane, and Schmude did not have the authority to put it there. Someone else did, and that someone was not a general, not a politician, not an aircraft company executive. He was a civilian test pilot who worked for an engine manufacturer. And he was about to change the war because he spent 30 minutes in a cockpit and paid attention to what the airplane was telling him. On April 30th, 1942, at a Royal Air Force airfield in Duxford, England, a man named Ronald Harker climbed into an Allison-powered Mustang Mark I and took off. Harker was a test pilot for Rolls-Royce, the company that built the Merlin engine. He was not military. He held no rank. He had no authority over procurement decisions or production schedules or strategic planning. What he had was a deep, experienced understanding of how airframes behaved in flight, built over years of testing different aircraft types for the engine manufacturer. He had flown Spitfires. He had flown Hurricanes. He had flown a wide range of British and American designs, evaluating how each airframe interacted with its power plant. He was at Duxford because of one man's initiative. Wing Commander Ian Campbell Ord, the commanding officer of the RF's Air Fighting Development Unit, had been evaluating the Allison Mustang and had reached the same conclusion every other evaluator had reached. brilliant below 15,000 feet, hopeless above it. But Campbell Ord had done something that none of the other evaluators had thought to do. He had invited a Rolls-Royce test pilot to come out and fly the Mustang for himself, not to evaluate the engine, to feel the airframe. Harker flew the Mustang for 30 minutes, and in those 30 minutes, he understood what Schmude had built. The airframe was extraordinary. Harker had flown dozens of different fighter types, and the Mustang was cleaner, smoother, more aerodynamically refined than any of them. The controls were harmonized in a way that most fighters of the era could not match. The drag was startlingly low. At every speed below the Allison's altitude ceiling, the airplane did things that airplanes with that engine were not supposed to be able to do. It was faster than it should have been. It was more efficient than it should have been. It handled with a precision that Harker, a man whose entire career was built on evaluating aircraft, immediately recognized as exceptional, and it was being strangled by its own engine. Harker landed. He had already composed the most important memo of his career in his head before the wheels touched the runway. His formal assessment, documented in his report to Rolls-Royce and preserved in the records at Hucknall, the Rolls-Royce Flight Test Center, was direct. The Mustang airframe was among the finest he had ever flown. Below 15,000 feet, it was better than the Spitfire. What it needed was the Rolls-Royce Merlin 61, the new engine fitted with a two-stage, two-speed supercharger, the same engine that had transformed the Spitfire Mark V into the Spitfire Mark IX. That engine, Harker argued, placed in this airframe, would produce a fighter without equal at any altitude. Harker was the first person outside North American aviation to see what Schmude had actually built. He was the first person to understand that the airframe's superiority at low altitude was not accidental. It was the product of the radiator duct and the wing profile doing exactly what Schmude had designed them to do. And if you took away the Allison's altitude ceiling by replacing it with a Merlin that could breathe at 30,000 feet, the same aerodynamic advantages that made the Mustang dominant at low altitude would make it dominant everywhere. Harker did not have the authority to order the conversion. He was a civilian test pilot. His memo went to Rolls-Royce management. From there, it went to the Ministry of Aircraft Production. The path from a test pilot's recommendation to an actual program involved layers of bureaucracy, institutional resistance, competing priorities, and the simple inertia of large organizations at war. The memo could have died in a filing cabinet. It nearly did. What saved it was sustained lobbying at the highest levels. Major Thomas Hitchcock, the American assistant military attaché in London, became one of the most persistent advocates for putting the Merlin into the Mustang. Hitchcock had access to senior officials on both sides of the Atlantic. He pushed the idea relentlessly. Others pushed with him, and eventually, the combined weight of Harker's technical assessment and Hitchcock's political persistence broke through. The British moved first. Rolls-Royce took 5 Allison Mustang airframes and began the conversion to the Merlin 65 engine. These experimental aircraft were designated the Mustang X series. On October 13, 1942, Captain R. T. Shepard, Rolls-Royce chief test pilot, took the first Mustang X into the air from the flight test facility at Hucknall. The transformation was immediate and dramatic. The airplane that had been gasping at 25,000 feet climbed past 1,000 and kept going. Level speed at altitude reached 430 miles per hour. The Mustang X was faster than the Spitfire Mark IX at every altitude. It was faster than the Focke-Wulf 190. It was faster than anything the Luftwaffe had in operational service. the airframe that Schmude had designed. The airframe, built around a radiator duct that was supposed to be a mistake, and a wing that was supposed to be a gamble, had been waiting for this engine. The Merlin did not improve the Mustang. The Merlin revealed it. On the other side of the Atlantic, Schmude's own engineering team at North American Aviation had reached the same conclusion independently. They had begun converting two P-51 airframes to accept the Packard-built V-1653, the American license-produced version of the Rolls-Royce Merlin. On November 30th, 1942, Robert Chilton, the same test pilot who had rebuilt and flown the crashed NA-73X prototype 2 years earlier, took off from Mines Field in the first XP-51B. He climbed past 30,000 feet. The engine was pulling hard. The airframe was clean. The instruments were showing numbers that nobody at North American had ever seen on a single-engine fighter. And then the cooling system failed. A chemical reaction between the ethylene glycol coolant and dissimilar metals in the plumbing had deposited a layer of crystalline scale across the radiator matrix. The carefully designed Meredith duct, the duct that Schmude had computed to the inch, was being choked by a chemistry problem that no aerodynamicist could have predicted. Chilton saw the temperature gauges climbing. He saw white smoke beginning to trail from the belly. He brought the airplane down. But before the cooling failure stopped him, Chilton had recorded a level speed of 441 miles per hour at 29,800 feet. That was more than 100 miles per hour faster than the Allison Mustang at the same altitude. The rate of climb had approximately doubled. The airplane, even with a failing cooling system, had just demonstrated that it was the fastest propeller-driven fighter in the world. The United States Army Air Forces did something uncharacteristic. They ordered 400 Merlin-engined P-51Bs in August of 1942. 3 months before the first XP-51B had even flown, the brass had seen the Allison Mustang's performance data and calculated what the known output of the Merlin would do inside the same airframe. They were placing a bet on Schmude's design before it had proven itself with the new engine, because the airframe had already proven something else. It had proven that its disastrous understood aerodynamics at a level that most of the aviation industry had not yet reached. But the belly duct had one more problem to solve. Schmude's original design, the duct that had been wind tunnel, tested at Caltech and computed against Meredith's mathematics, had a subtle flaw that only appeared at high speed. The intake was mounted too close to the fuselage skin. At high speeds, every aircraft develops what aerodynamicists call a boundary layer, a thin blanket of slow-moving turbulent air that clings to the skin of the fuselage like a second skin. At low speeds, the boundary layer is thin and irrelevant. At the speeds the Merlin Mustang was now reaching, the boundary layer was thick enough to matter, and the belly scoop, mounted flush against the fuselage, was swallowing that turbulent boundary layer air along with the clean free-stream air it was designed to ingest. The turbulent air disrupted the carefully engineered flow inside the duct. The diffuser could not slow the air smoothly. The radiator matrix received uneven airflow, and the pilots reported a deep rhythmic vibration that shook the entire airframe at high speed. They called it the rumble. The fix, when it came, was documented in the NACA test reports and was almost embarrassingly simple. The engineers moved the scoop down, away from the fuselage skin, by approximately 1.5 to 3 inches. A small gap, a trivial distance. But that gap allowed the slow boundary layer air to slip past the intake instead of being swallowed by it. Clean, free-stream air entered the duct. The rumble disappeared, the duct efficiency improved. Schmude was not a perfect engineer. He had gotten the boundary layer spacing wrong. But the way he fixed it, measuring the problem, identifying the root cause, applying the minimum necessary correction, that was the pattern that defined his entire approach to the Mustang. He did not build an airplane by being brilliant once. He built it by being methodical every single day, solving one problem at a time, never panicking, never abandoning the design, never retreating from the fundamental decisions he had made about the radiator and the wing. When something went wrong, he fixed what was wrong and kept the rest. By the spring of 1943, with the boundary layer problem solved, with the Merlin engine mated to the airframe, with the duct performing as Schmude had computed, the P-51B was ready. Production was ramping up at the Inglewood factory, but the airplane would not reach combat units in England for another 9 months. And on the other side of the Atlantic, the reason it was needed was being written in the blood of bomber crews who were dying at a rate that could not be sustained. The United States Army Air Forces had committed to a strategic doctrine that sounded rational in a briefing room and was catastrophic in practice: daylight precision bombing. The theory was that heavily armed formations of B-17 flying fortresses, bristling with defensive machine guns, could fight their way to targets deep inside Germany in broad daylight, bomb with precision, and fight their way back. The theory assumed that the bomber formations could defend themselves without fighter escort. The theory was wrong. Through the summer and fall of 1943, the 8th Air Force, based in England, sent its bomber groups deeper and deeper into German-held airspace. And the Luftwaffe, which had spent 2 years studying the B-17's defensive blind spots, was waiting for them. German fighter controllers tracked the bomber formations from the moment they crossed the coast. They vectored interceptors to hit the formations from angles that minimized exposure to the defensive guns. Head-on attacks at closing speeds of over 600 miles per hour. Frontal assaults that gave the B-17 gunners less than 2 seconds to acquire, track, and fire. The German pilots were experienced. Many had hundreds of combat sorties. They knew exactly how to kill a flying fortress. In October of 1943, the 8th Air Force's losses crossed a threshold that every planner understood was unsustainable. More than 9% of bomber sorties were ending in destruction. For every 100 heavy bombers that took off from English airfields, 9 were not coming home. Another 45 would return with battle damage. Engines shot out, hydraulics severed, crew members dead or wounded in their positions. On a single day, October 14th, 1943, the 8th Air Force launched a deep penetration raid against the ball-bearing factories at Schweinfurt in central Germany. 60 B-17 flying fortresses were shot down, 60 aircraft, 600 men killed, captured or missing. The crews who survived called it Black Thursday. The commanders who planned it called it the worst single day of the air war. The problem was not the bombers. The problem was not the crews. The problem was range. American fighter escorts, primarily the Republic P-47 Thunderbolt, could accompany the bombers only partway into Germany. The P-47 was a powerful airplane. It had a massive radial engine. It could fight well at high altitude, but it drank fuel at a rate that emptied its tanks before the bombers reached their targets. At the German border, sometime sooner, the P-47s turned back. The bombers flew on alone, and the Luftwaffe, which had been tracking the fighter escort on radar, waited for exactly that moment. The moment the escorts turned for home was the moment the attacks began. The Spitfire had even less range than the Thunderbolt. No single-engine Allied fighter in on 1943 could escort heavy bombers to targets deep inside Germany and fly back. Physics would not allow it. The fuel mathematics would not allow it. That was the consensus. But the consensus was built on an assumption. It assumed that every fighter paid the same cooling penalty. Every fuel calculation in every air force in the world started from the same baseline, that roughly 40% of a liquid-cooled fighter's thrust was consumed by cooling drag, and therefore every range estimate hit the same wall. No designer had found a way around that wall. No designer had tried to turn the wall into a door, except one, and his solution had been sitting in the files at North American Aviation since 1940, built into an airframe that the world had written off as a low-altitude reconnaissance aircraft. That was why Hermann Goering had made his public declaration that no Allied fighter would ever escort bombers over the Reich. His touch insiders left the range limitations of Allied fighters based on conventional airframe design, conventional cooling system, conventional drag budgets. What they did not account for, what they could not account for, was that Schmidt's belly duct had broken the equation. Earth recovered the vast majority of the cooling drag as thrust. An engine that does not fight its own cooling system burns less fuel per mile. An airframe with lower net drag covers more distance on the same amount of fuel. The P-51B, fitted with the Merlin engine and carrying two external drop tanks of 108 gallons each, could fly from bases in England to Berlin and back, over 700 miles into enemy territory. A round trip of more than 1,100 miles with fighter escort the entire way. The laminar flow wing contributed to the same equation. The NAC airfoil that Schmidt had selected, even in the turbulent boundary conditions of a production aircraft, produced less drag at cruise speeds than any conventional fighter wing of the era. Less drag meant less fuel burned per mile. Less fuel burned per mile meant more miles of escort range. Schmidt's radiator, Schmidt's wing. Two engineering decisions that had been dismissed as mistakes, both reducing drag, both extending range, both feeding into a fuel equation that Goring's analysts had calculated, was impossible. By the time the 8th Air Force was bleeding to death over Schweinfurt, the solution was rolling off the production lines at Inglewood. The P-51 Merlin Mustang, the only fighter in the world whose designer had thought about the airplane as a system rather than a collection of parts, and whose system-level produced that could solve the rain problem, killing the daylight bombing campaign. On December 1st, 1943, the 354th Fighter Group, a brand new unit, freshly trained in California and now based in England, flew its first combat mission in the P-51 Mustang, a fighter sweep over France. No contact with the enemy. On December 5th, they escorted bombers to Amiens. On December 11th to Emden. On December 13th, they pushed 480 miles into German airspace. For the first time in the European Air War, heavy bombers flying daylight missions had single-engine fighter escort the whole way to the target and back. On January 11th, 1944, a lieutenant colonel named James Howard climbed into a P-51 that he had named Ding Hao, a Chinese greeting he had learned, while flying with the American volunteer group in China before the United States entered the war. Howard was 30 years old. He was escorting B-17s on a deep penetration raid toward Oschersleben in central Germany when he became separated from his wingman and his squadron. he found himself alone above a formation of heavy bombers, with more than 40 German fighters pressing attacks from every direction. Messerschmitts and Focke-Wulfs hitting the bomber boxes in coordinated waves, the way the Luftwaffe had practiced for 2 years, the way that had killed 60 bombers over Schweinfurt 3 months earlier. James Howard did not turn for home. He did not climb away to wait for his squadron to reform. For 30 minutes, according to the Medal of Honor citation that was later confirmed by the crews of the B-17s who watched it happen, he engaged Luftwaffe fighters single-handedly. He shot down 3. He damaged a 4th. He broke up successive attack runs on the bomber formation below him, diving through formations of German fighters, firing, pulling up, rolling back in. The B-17 crews, when they landed back in England, described what they had seen. A lone silver fighter had positioned itself between them and the German attackers and had refused to leave. Some of the bomber crews thought it was multiple fighters. It was one man in one airplane. Howard became the only fighter pilot in the European theater of operation to receive the Medal of Honor. And the reason he was able to fight for 30 minutes over central Germany, deep inside the Reich, far beyond the range where any P-47 would have already turned for home, was that Schmud's duct gave his airplane the fuel efficiency to remain. The thrust recovery that Meredith had predicted and Schmud had engineered into the airframe translated into enough fuel in the tanks to stay and fight when any other fighter would have had to leave or crash. Howard's Medal of Honor was written in the physics of a radiator duct. 1 month later, the 8th Air Force launched Operation Argument, the campaign the historians would later call Big Week. From February 20th through 25th, 1,944, 6 consecutive days of maximum effort, the 8th Air Force sent every bomber it had against the German aircraft industry. Ball-bearing plants, airframe factories, engine works, assembly facilities across central and southern Germany, and the Mustangs went with them every mile. According to statistics compiled at the National World War II Museum, during those 6 days, Mustang pilots destroyed approximately 17% of the Luftwaffe's experienced combat fighter pilots in air-to-air combat. 17% of the trained, battle-hardened fighter pilot corps of a major industrial power in 6 days. And here is where Schmud's second decision, the laminar flow wing, proved its worth in a way that Schmud himself had not fully anticipated. The air combat during Big Week was fought at extreme altitude, 25,000 feet, 28,000, 30,000 and above. At those altitudes, the air is thin. Aerodynamic forces behave differently, and every fighter aircraft encounters a speed limit called the critical Mach number, the speed at which airflow over some part of the wing reaches the speed of sound and begins creating shock waves that destroy lift, increase drag, and make the airplane nearly uncontrollable. The Messerschmitt Bf 109 hit its critical Mach at approximately 0.75. The Focke-Wulf 190 was similar, roughly 0.75. Above 30,000 feet, in the thin air where true airspeed is much higher than indicated airspeed, German pilots pushing their throttles forward would hit the compressibility wall and feel the controls go heavy. The airframe shudder, the airplane refused to go faster. They could not pursue a target that was pulling away. They could not dive without risking loss of control. The Mustang's critical Mach number was approximately 0.78, 0.03 of a Mach number higher. On paper, that looks trivial. In a fight at 30,000 feet, it was the difference between catching the enemy and watching him pull away. It was the difference between following a diving target and having to break off because the controls were too heavy. It was 30, 40, or 50 miles per hour of additional usable speed at the altitudes where the war's most critical battles were being fought. And it came from the wing, not from the engine, not from the armament, from the shape of the airfoil that Schmude had selected 3.5 years earlier in a drafting room in Inglewood, California. But here is the part of the story that turns the entire Mustang narrative into something stranger and more instructive than a simple tale of engineering success. After the war, the National Advisory Committee for Aeronautics conducted extensive studies on the Mustang's wing. They tested production aircraft. They measured the boundary layer behavior on actual combat-used airframes. And what they found would have satisfied every critic who had ever doubted the laminar flow concept. The Mustang's wing never achieved true laminar flow in operational service. Not once. Not on any production aircraft. The surface finish on factory-built Mustangs, the rivet heads standing a fraction of an inch above the skin, the panel seams where fuselage sections joined, the paint, the accumulated oil and exhaust residue, the patches over bullet holes, all of it was more than enough to trip the boundary layer from laminar to turbulent flow far earlier than the theoretical airfoil shape predicted. The wing that Schmude had designed specifically to maintain laminar flow failed at that specific purpose under every real-world condition it encountered. The laminar flow promise was broken. Schmude's second bet appeared to have lost, except it had not lost. It had won something different, something larger, something that Schmude may have suspected from the beginning. The airfoil shape that produced laminar flow in a wind tunnel, the shape that required mirror-smooth surfaces to work as designed, happened to be, entirely apart from its laminar flow properties, one of the finest high-speed airfoil profiles ever put on a fighter aircraft. Even with a fully turbulent boundary layer, even with the laminar flow completely gone, the NA-AKA 45-100 airfoil gave the Mustang a critical Mach number of 0.78 that was meaningfully higher than the BF-9 and FW-190 at 0.75. It was dramatically higher than the P-38 Lightning at 0.68 and the P-47 Thunderbolt at 0.71. The wing failed at the thing it was designed to do, and it succeeded at something its designer had not publicly promised it would do. A wing chosen for one purpose that delivered a different and more important purpose entirely. That was the real pattern of the P-51 Mustang. A radiator duct that looked like a drag disaster and turned out to be a thrust source. An engine that was wrong for the mission until the right engine arrived and revealed that the airframe had been the best in the world all along. A wing that never achieved its stated purpose and achieved a different purpose that won battles the designer had not known he was planning to win. 3 surprises. And behind all 3, one quiet, methodical engineer who had been willing to follow the mathematics to conclusions that the rest of the aviation industry was not ready to accept. But the mathematics of the P-51 Mustang were about to be tested in a way that no wind tunnel and no engineering report could prepare anyone for. Because in the spring of 1944, the airplane was about to do the thing that Göring had declared impossible. And the men who flew it were about to discover that even the finest engineering in the world could not protect them from the thing that war does to the people who fight it. On March 4th, 1944, the 4th Fighter Group, based at Debden in England and commanded by Colonel Don Blakesley, a former Eagle Squadron pilot who had been fighting the Luftwaffe since before America entered the war, flew P-51 Mustangs to the Berlin area for the first time. Berlin, the capital of the Reich, 1,100 miles round trip, 30,000 feet. Fighter escort the entire way. The 354th Fighter Group went with them. The two groups, flying the airplane that 3.5 years earlier had been a set of drawings, Schmood's drafting table, crossed the North Sea, crossed the German border, crossed the industrial heartland of the most formidable military power in Europe, and arrived over the city that Göring had publicly sworn no Allied fighter would ever reach. Göring had made that promise because the mathematics supported it. Every calculation his intelligence services had run, every fuel consumption model, every range estimate based on known Allied fighter designs, confirmed that a single-engine escort fight with the range to reach Berlin and return was a physical impossibility. The numbers did not work for conventional fighters. The Mustang was not a conventional fighter, and the numbers had been rewritten by a designer who understood that an airplane is not a collection of components, but a system, and that a system designed whole will outperform any set of individually optimized parts. According to the transcripts of his 1,945 interrogation, Göring reportedly told his American interrogators that when he saw Mustangs over Berlin, he knew the jig was up. He recognized the consequence. He never grasped the cause. In January of 1944, 2 months before those Mustangs appeared over Berlin, General Jimmy Doolittle had taken command of the 8th Air Force and issued an order that overturned everything American fighter doctrine had assumed about the role of escort fighters. Before Doolittle, fighters were ordered to stay close to the bomber formations, fly alongside them, protect them. Do not leave the bombers. Doolittle reversed the doctrine completely. Under his new order, fighters were released. Their mission was no longer to orbit the bomber stream and wait for attackers. Their mission was to go hunting, find the Luftwaffe wherever it could be found, at altitude, on the deck, on the airfields, in the traffic pattern, and destroy it. The bombers were bait. The fighters were the weapon. This order was only possible because of one airplane. No other Allied fighter had the range to sweep ahead of the bomber stream, engage German interceptors deep inside the Reich, fight at full power for the duration of an engagement, and still have enough fuel to escort the bombers home. The P-47 could not do it. The Spitfire could not do it. Only the P-51B, with its Merlin engine and its Meredith duct and its high-speed wing, could execute Doolittle's doctrine without running dry over enemy territory. Doolittle's order transformed the air war. The Mustang groups stopped defending and started attacking. And in the spring of 1944, the results came in faster than anyone on either side had anticipated. Captain Don Gentile was 23 years old. His wingman, Lieutenant John Godfrey, was roughly 22. They flew together out of Debden with the 4th Fighter Group, and in the early months of 1944, they became the most publicized fighter pilot team of the war. Between them, they accounted for more than 30 German aircraft in a span of weeks. Eisenhower called Gentile a one-man air force. The Luftwaffe reportedly called them the Debden Gangsters, and Göring was said to have offered to trade entire squadrons for their capture. They were not anomalies. They were the product of an airframe that gave its pilots an advantage at every altitude, in every phase of combat, against every opponent the Luftwaffe could put in the air. The P-51B was faster than the Bf-109G in level flight. It was faster than the FW-190A at high altitude. It could dive with either and pull out when either would have hit compressibility. It could stay over the target when every other Allied fighter had already turned for home. The airplane did not make average pilots into aces, but it gave skilled pilots a machine that did not limit them, and in the hands of men who understood what it could do, the results were devastating. But the Mustang's most complete pilot was not at Debden. He was flying with the 352nd Fighter Group, 487th Fighter Squadron, and his name was George Preddy. Preddy had been born on February 5th, 1919, in Greensboro, North Carolina. He was 25 years old in the summer of 1944. He was slight of build, quiet, methodical. He did not give dramatic interviews. He did not perform low passes for the cameras. He flew with the kind of systematic precision that his squadron commander, Major John C. Meyer, recognized as something rare. Meyer, who would eventually become a four-star general and the commander of Strategic Air Command, said of Preddy in remarks preserved in the 352nd Fighter Group records that George Preddy was the greatest fighter pilot who ever squinted through a gun sight. The complete fighter pilot. There is something worth pausing over in that description. The complete fighter pilot. Not the most aggressive, not the most daring. Complete. The word implies balance, discipline, the ability to see the entire fight, not just the target in front of the guns. Preddy flew the way Schmude engineered, quietly, without flash, with an attention to the whole picture that separated him from pilots who were braver or louder, but not as effective. On August 6th, 1944, Preddy was escorting heavy bombers in the Hamburg area when he spotted a formation of more than 30 Messerschmitt Bf-19s assembling to attack a box of B-17s. The German fighters were forming up for a coordinated assault, the kind of massed attack that had killed 60 bombers over Schweinfurt 10 months earlier. Preddy led his flight into the formation. In a single engagement, he shot down 6 Bf-109s. 6 confirmed aerial victories in one mission. It was a record for any pilot in a single engagement, and it held for the remainder of the war. Preddy's total score at the end of his combat career was 26 and 83/100ths aerial victories, according to the records compiled by the United States Air Force Historical Research Agency. The highest scoring Mustang ace of the entire war. He did not live to see the end of it. On Christmas Day, 1944, George Preddy was leading 2 other Mustangs at treetop level in pursuit of a Fokker-Wulf 190 near Liège in Belgium. The area had been cleared for their low-level chase. The ground controllers had coordinated the friendly anti-aircraft units along the route been notified that American fighter jets would be coming through at low altitude. But war is a system, and systems fail at their joints. Due to a documented communication breakdown, a United States Army Quad 50 anti-aircraft crew positioned in the area had not received the order to hold fire. They saw 3 aircraft coming in fast at treetop height. They could not identify them as friendly in the seconds available. They opened fire. All 3 Mustangs were hit. George Preddy, the highest-scoring Mustang ace of the Second World War, the complete fighter pilot, was killed by American gunfire on Christmas morning at the age of 25. Schmude had designed the most capable fighter aircraft of the war. He had given it a radiator duct that extended its range beyond anything the enemy thought possible. He had given it a wing that let it fight at altitudes where no other Allied fighter could follow. He had given it an airframe so clean, so aerodynamically refined, that it outperformed aircraft with more powerful engines and heavier armament. But no engineering decision, no matter how brilliant, protects a pilot from a communication failure between 2 friendly units on a Christmas morning in Belgium. That is the boundary where engineering ends and war begins. Schmude could design the system. He could not design the war. The German engineers who examined captured P-51 Mustangs in 1945 spent months trying to understand what had happened to them. They took the airframes apart, piece by piece. They measured the wing sections. They tested the airfoil profiles. They disassembled the Meredith duct and studied its geometry. They ran the numbers on the Packard Merlin engine, and they kept arriving at the same frustrating conclusion. No single component was overwhelmingly superior. The engine was a Packard-built copy of a British Rolls-Royce design. Good, but not revolutionary. The armament on the later production models was 650 caliber Browning machine guns. Effective but not exceptional. The top speed was 437 miles per hour at 25,000 feet. Competitive with the best German fighters, but not dramatically faster. The rate of climb, the turn radius, the roll rate, all of these were good, but none of them were so superior that they explained the catastrophe the Mustang had inflicted on the Luftwaffe. The German engineers kept measuring. They kept comparing individual specifications, and they could not find the answer. Because the answer was not in any individual specification. The answer was in the relationship between the specifications, in the way the airframe made the engine more efficient, in the way the engine made the airframe fly higher, in the way the radiator duct made the range longer, in the way the wing kept the entire system stable and controllable at speeds where other fighters lost control. Every component served every other component. Every engineering decision reinforced every other engineering decision. The cooling system was part of the propulsion system. The wing was part of the speed equation. The fuselage was shaped around the duct, and the duct was shaped around the physics of waste heat recovery. Every other fighter of the war had been designed the traditional way. The Spitfire, the Bf-109, the FW-190, the P-47, the P-38. Each was a collection of individually optimized subsystems. The best available engine, the best available wing, the most practical cooling solution. Each subsystem selected for its own merits and then assembled into an airframe. It was the way fighters had been designed since the First World War, and it produced excellent aircraft. The Mustang was designed the opposite way. It was designed as a whole. The airframe was not a container for the engine. The airframe was part of the propulsion system. The radiator was not a penalty to be minimized. It was a thrust source to be maximized. The wing was not just a surface to generate lift. It was a high Mach number profile that let the airplane operate efficiently in the thin air above 30,000 feet, where other fighters were burning fuel just trying to stay airborne. This was systems thinking before the term existed, and it was the product of one man's approach to engineering. Schmude did not design the best radiator. He did not design the best wing. He did not select the best engine. He designed the best relationship between radiator, wing, and engine, and that relationship, not any individual component, was what the German engineers in 1945 could not find because they were not looking for it. The side that thought about airplanes as systems won. The side that thought about airplanes as engines with wings around them lost. The final numbers deserved fed plainly. Approximately 15,600 P-51 Mustangs were built at a cost of roughly $50,000 each, cheaper than a P-47 Thunderbolt at $80,000, a fraction of the $150,000 each B-17 Flying Fortress cost. The 8th Air Force's bomber loss rate, which had exceeded 9% in October of 1943, the month of Black Thursday, fell below 3.5% by February of 1944, a matter of weeks after the Merlin Mustangs arrived in quantity. Deep daylight penetration raids into the heart of Germany went from suicidal to routine. The P-51 groups of the 8th, 9th, and 15th Air Forces claimed approximately 4,950 German aircraft destroyed in air-to-air combat, and another 4,131 destroyed on the ground. Roughly half of all United States Army Air Force's aerial victory claims in the European theater, according to the Consolidated Combat Records. More kills claimed by any single Allied fighter type than any other in the war. The Luftwaffe had not been outproduced. That is a critical point. German fighter production actually peaked in 1944, despite the bombing campaign. The factories were dispersed. The assembly lines kept running. New Bf-109s and FW-190s rolled out of German plants by the thousands. But the pilots who flew them were dying faster than they could be trained. The Mustangs were killing experienced pilots in the air, week after week, month after month, until the replacement pilots arriving at Luftwaffe fighter units had so few flight hours, so little combat training, so little experience against skilled opponents, that the kill ratios became lopsided. By the summer of 1944, Mustang pilots with a few months of combat experience were engaging German pilots with a few weeks of flight training. The outcome was predictable, and it was not close. In his 1945 interrogation, Göring reportedly told his American interrogators that long-range fighter escort was the decisive factor in the air war. He had built the Luftwaffe from nothing. He had promised it would shield the Reich from the sky. And now he was sitting across a table from the men who had destroyed it, unable to explain how a single-engine American fighter had done what his own analysts had calculated was physically impossible. The answer was never in the engine. It was never in the guns. It was in a radiator duct designed around a 1935 British paper that the rest of the world had ignored, and in a wing whose most important property was one its designer had never publicly advertised. Don Gentile went home after crashing his P-51 during a low pass in front of press photographers at Debden on April 13th, 1944. He was sent on a war bond tour and never returned to combat. Ronald Harker, the Rolls-Royce test pilot, whose 30-minute flight at Duxford had set the entire Merlin conversion program in motion, continued testing engines for Rolls-Royce and died in 1999. George Preddy was 25 years old. Edgar Schmude stayed at North American Aviation. He did not go on bond tours. He did not give interviews to newspapers. He went back to his drafting table and continued designing airplanes. He led the design team for the F-86 Sabre, the swept-wing jet fighter that would dominate the skies over Korea a decade later. Another airplane, another set of engineering decisions, another quiet revolution that the public would attribute to the pilots and the generals and the politicians, not to the man at the drafting table. Schmude died in 1985. He is not a household name. Most Americans have never heard of him. If you walk through an aviation museum and stop in front of a P-51 Mustang, the placard will tell you about the airplane's speed, its range, its kill record, its role in the air war. It will probably not mention the name of the man who designed it. It will almost certainly not mention the name of the British engineer whose 1935 paper made the belly duct possible. Frederick William Meredith never received any particular public recognition for his work. His paper, R&M 1683, remains one of the most consequential technical documents in the history of aviation. It described a principle that transformed a cooling penalty into a propulsion advantage and made possible the range that broke the Luftwaffe. Meredith died without the aviation world fully acknowledging what that single dry mathematical report had done. Meredith, Schmude, Atwood, Hawkey, Harker. These are not names that appear in the popular histories of the Second World War. Goring's name appears. The airplane itself, silver and gleaming at air shows, engine rumbling, crowds gathered behind the rope line. That appears. But the Mustang was not built by the aces who flew it. It was not built by the Reichsmarschall who failed to stop it. It was built piece by piece, calculation by calculation, by quiet men who looked at three engineering problems that the entire aviation industry had decided were unsolvable, and solved all three, not by being brilliant in a single flash of inspiration, by being willing to follow the mathematics to a place where the mathematics said something that no one else was willing to believe. A radiator that produces thrust instead of drag. An engine that is wrong for its airplane until someone puts the right engine in the same airframe and discovers that the airframe was the best in the world all along. A wing that fails at the one thing it was specifically designed to do and succeeds at a different thing that its designer suspected but never promised. Three engineering choices that looked like errors. One airplane that, because of those choices, not despite them, arrived over Berlin in the spring of 1944 and told the most powerful air force in Europe that the war was over. The men who flew the Mustang are nearly all gone now. The last Second World War fighter pilots are in their late 90s, or past 100. The airplanes they flew are museum pieces, airshow warbirds, photographs in books that fewer people open every year. But the idea that built the airplane, the idea that a system designed as a whole will defeat a collection of parts no matter how good each part is on its own, that idea is not in a museum. It is the single most important engineering lesson of the air war over Europe, and it was written down first in a dry British technical paper in 1935 by an engineer nobody remembers, built into an American airframe in 102 days in 1940 by a quiet man at a drafting table nobody remembers, and unlocked by a 30-minute test flight in 1942 by a civilian pilot nobody remembers. Three choices, three men, one airplane, the end of the Luftwaffe.